Welcome to Spring LIB.
Okay, we've been shown the following skeletal structure. And we've been asked a few questions about this oxygen, as well as this carbon, as well as we've been asked to sort of complete this structure. So the first thing you may notice is that this carbon here does not have a full octet, right? We know carbon doesn't really bear lone pairs, so it's more than likely that one of these bonds is going to have to be a double bond. We may also know that this oxygen only has one bond, and that oxygen typically wants to have two bonds and two lone pairs. So we can sort of solve both problems just by adding a double bond there. Solve both problems just by adding a double bond there. And now we've got a fairly reasonable electron dot structure of this molecule, a complete electron dot structure, if you will. We may also consider that there's a pair of lone pairs there, a couple lone pairs there, and we should be good to go. Okay, question B, what is the molecular shape around the oxygen with an asterisk? That's this right here, right? Okay, well, it's basically going to be like water, okay? Recall that in terms of electron geometry, this is tetrahedral, right? But since we have two lone pairs, right, in terms of molecular geometry, that's going to give us a bent geometry. So the molecular shape around oxygen is going to be bent, and if you recall, bent bond angles, like in water, correspond to a roughly 104.5 degree bond angle. If they're telling you that's wrong, then that means they're looking instead for tetrahedral and 109.5. But more realistically, it's bent. It's just they're not being super specific. When they say ideal bond angle, right? In actual fact, it's bent and it's 104.5. In terms of electronic geometry, it's tetrahedral 109.5. But if you actually, made a model of this molecule and computed it, Okay. Next one's not so bad because ideal and actual are the same. So this carbon, as you may recognize with its double bond, is sp2 hybridized. sp2 hybridized carbons, or carbons with three bonds or three bonding regions, are trigonal planar. So the molecular shape is going to be trigonal planar. That's true both of the electron geometry and the molecular geometry. No ambiguities here like there were there. And the ideal bond angle in trigonal planar is 120 degrees, like a triangle, basically.